Okay. We actually have plenty of time for this particular test, so I'm going to digress quite a bit today. So we aren't going to cover that much material today because we don't have to, and we're probably still in early every day. So the next test is very small, 5.2, 5.3, 5.4. I'm even throwing some problems out from 5.2. So if you look at your original list, there was a 35 and 37. Throw those out. I don't want to do those. So we're just doing 1 to 19 odd, which is not that long. Okay. And I'm figuring if I devote 2 days for each of these, we'll still have plenty of time. Okay. So if I do 2 days here, Wednesday's a holiday. It's a one-day weekend for Veterans Day. 2 days here and 2 days here. I still have, plenty of time to do what we need to do. Okay, so the next exam will be Friday the 20th. So this coming Friday, it'll just be a quiz. Okay, then after that, we just have 1 chapter left for 3 weeks. And then we're done. Okay, in fact, these two combine, the hardest test and the hardest chapter was the trig. And these two combined, looks like it may be even fewer sections in all of this combined. Okay, but be that as it may. All right, so that's where we're at. So I'll do 5.2. I'll do not that much of 5.2 today. So we'll probably finish early every day, but from here on up until here. But we'll see how it goes. Okay. Now I need to blab on some other things because I think I have the time. I'm going to go over some things about the test because I think we needed to. Okay, so I gave you the test. You should have your test score back, but some things to go over quickly. Number 1, common mistakes were not changing it to radians. Okay, the formula S equals R theta only works in radians, and you had to label units. So some of you are wondering, why did I lose points on this and whatever? It's supposed to be feet. Okay, so you should have at least shown me 9 pi over 4. If you left your answer as 9 pi over 4, I accepted it. But if you went ahead and changed it to a decimal, that's okay too. You had to give me feet. Okay. Number 2, I couldn't accept it if you didn't show me any work. Okay, you need to show me how you got the square root of 15. Okay, and then go from there. And also, you can't just put sine, cosine, tangent, sine theta, cosine theta, tangent theta. Some of you, I let it slide on quizzes, but I mentioned before, if I let it slide on quizzes, or sometimes on a quiz, I might say, okay, you got the full credit, but make sure you put the theta or whatever. Okay, and it won't be as nice on tests, and it wasn't. Okay, number 3, it said round to the nearest whole number, so you needed 75 feet, not 75 point whatever. Okay. 4, I accepted it if you just went straight to the answer, but a unit circle would work. 5, I definitely would not accept it if you just gave me this. I have no idea how you came up with that. Okay, so I showed you on the video how to do that. You should show me the calculations for how you do it. And you should do something similar to what we did in class. So some of you did some pretty interesting stuff that was completely different than what we did in class. Good rule in general, not just for my class, but classes in general, do it the way the teacher wants it, right? Instead of making up your own thing, because the teacher may not accept it. And I didn't accept it for some of this because I didn't go over some of those. Okay, 6 was pretty straightforward. You got the amplitude, the period, and the shift, the pi to the right and 1 up. Okay. Likewise, for 7, I needed to see some explanation of how you came up with the cosine. Okay, so don't come to me just asking for more points because your last thing that you wrote matched the last thing that I wrote. And all the in-between stuff has to match also. Okay, so show me some justification that once you have the sine, let's say, that you come up with the cosine. And I'll show you how to do that in the video. Okay. Number 8, I got some pretty interesting ways to come up with it. You had to do it the way we did it in class, which was change sine of 2x, change cosine of 2x. It's on the video. Okay, so I accepted only those ways. Number 9, again, I needed to see some work, especially like the showing of a triangle. Okay, so you should show me something like this, or use the fact that cosine squared plus sine squared equals 1. Some of you had some pretty interesting ways of doing it, but you had to do it the way we did it in class. Okay, so again, I don't accept your answer just because the last thing you wrote was 7 over 25. The last thing I wrote is 7 over 25. Again, let's distinguish between answer. Okay, the answer is not 7 over 25. Okay, the last thing that you write is 7 over 25. The answer is showing me this and 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 7 over 25. The answer is not 7 over 25. The last thing you write is 7 over 25. So if the last thing you write is 7 over 25 and the last thing I wrote is 7 over 25, it doesn't mean it's correct. Okay, the answer is all of this. Okay, so distinguish again between the last thing you write, which a lot of people consider the answer. No, the answer is you have to show me all this stuff. Okay, and 10, pretty much the same thing. You should show me a picture and your calculations. And again, I don't accept it if you only show me this. This is the last thing you write, but this is not the answer. The answer is you show me this work, you show me the law of sines, blah, 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 blah. And that's what you get. Okay, this one I didn't say how to round off, so you could have rounded off anywhere. 7.04, 7.1, in some cases 11.3. That would have been fine for me also. Okay. All right, so those are just extra things I need to say about the test. Okay, Math Jam. Okay, I gave you on announcements over the weekend advertisement for CSM Math Jam. It's the first full week of January. I think it's January 4th through 8th of 2021. Yeah, I know it cuts into your vacation. You don't want to cut short your vacation maybe, but it's a nice little preparation for the next semester. So if you're willing to give up part of your holiday, your vacation, and sign up for Math Jam, it's free, absolutely free, to get you prepared for next semester. And speaking of next semester, some of you are asking, yes, I am teaching Math 251, which is the course after our class, and I just realized it's the same time, so it's 9 to 10. So I'll be conducting a class sort of like I'm doing this semester, but I'm going to tweak some things, but I won't give away what that is yet because I might change my mind. Okay, so, but I'm planning to teach Calc 1. I'm pretty sure it's the same time, 9 to 10. Same format. I'll be using my projection screen and all this, and quizzes on Fridays and exams on Fridays and so forth. So yes, I am the teacher for 251, or one of the teachers for 251. But you can see the schedule for other teachers also in case you find out, you don't want to take me or whatever. But yeah, I plan to teach 251 in a similar fashion to what I'm doing this semester. And I noticed at the same time, maybe they made it the same time figuring, okay, if you guys like this time and so forth, and just follow the same pattern for spring 2021, right? 9 to 10 for Calc 1 and so forth, okay? All right, so that's that, and I will get started now. And if you have questions, feel free to ask it. You can start putting in the chat, about anything I said. Question about the test, question about Math Jam, or a question about Math 251. You can bring those up. Okay, otherwise I'll get started with some of 5.2. I won't go that far. It's mostly introductory material, and I'll do a lot more problems tomorrow. Okay, and Wednesday we have a one-day weekend, 2 days for 5.3, 2 days for 5.4, and even if I fall behind, we're still going to be okay. Okay. Unless, again, I preface it, quote unquote, everything goes okay. You guys know my internet was down the whole week already and so forth, so we'll see how it goes. Okay. All right, so now I'll get started on chapter 5, which is on exponential and logarithm functions, which you should have seen already in Math 120, exponential and logarithm functions. So we're just going to rehash some of those ideas. All right, so on page 281, let me check something, sorry. Make sure, yeah, I am recording. Okay, so I'm good there. Okay, let's see. I had to make sure that I was recording, and I am recording. So let me get back to where I was. All right, so the exponential function. Okay, so exponential functions look like f of x equals a to the x power. Okay, a is the base. Okay, and for now, we're only allowing a to be positive and not equal to 1. If a is 1, you have 1 to the x power. That's just 1. That's too cheap. So we're not going to allow for that. It's only positive bases, but not 1. That's called an exponential function. So notice the variable is floating up here as an exponent, and there's a constant here. Okay, so that's called the exponential function. What do exponential functions look like? Okay, so here's some examples for a greater than 1. So you can plot a whole bunch of points. They've got them all here. Okay, so if a is bigger than 1, looks like this. So they got 5/4 to the x power, 7/4 to the x, 2 to the x, 3 to the x, 5 to the x. Okay, so it looks like when x gets big, y gets big. When x approaches infinity, y approaches infinity. But when x approaches negative infinity, it looks like the function approaches 0. They all generally look like that. They're all increasing. Okay, they all go up. And as you might guess, the bigger the base, the sharper it is. So look at the progression. That's the base of 5/4, 7/4, 2, 3, 5. So the bigger the base, the faster it goes up, which actually makes sense. I mean, just think about plugging in a number like 1. If I plug in 1, this gives me 5/4. This is 7/4, which is a little higher. This is 2, which is higher. This is 3, which is higher. This is 5, which is higher. So it makes sense that it goes like that. But notice on this side, they reverse. Okay, so notice here the green one was on top, but here the green one's on the bottom. And on this side, the red is on top, but the red is on the bottom. So they flip, okay, at the point 0, 1. It looks like they all pass through 0, 1. And that makes sense because take a look at a to the x. No matter what the base of a is, as long as a is positive, a to the 0 is always 1. So they all go through the same point, 0, comma 1. Okay, with the property that they're all increasing, they're all shooting up. Okay, so when x goes to infinity, y goes to infinity. When x approaches negative infinity, the y values approach 0. Okay, and that makes sense because let's say 2. Okay, if I plug in a super big number like 1,000,000, 2 to the million, that's really, really, really large. That shoots up. But how do you interpret 2 to the negative million? 2 to the negative million is 1 divided by 2 to the million. That's 1 divided by a super big number, which is a super small number. So that's why all of these go like that. So you can see they all pass through the point 0, comma 1. Okay, so a to the x approaches infinity. That's y approaches infinity as x approaches infinity. And then a to the x approaches 0 as x approaches negative infinity. So x goes way out here. The y values all approach 0. Okay. Okay, now they're trying to show us here what happens for the base between 0 and 1. Okay, we're not going to consider negative bases. Okay, only positive bases. Oh, there we go. This is focused a little bit better, but I have to raise it up. Okay, base bigger than 1, increasing. Base less than 1, decreasing, goes like that. But it still goes through 0, 1. Figure 2. Where am I? Page 282. So look at what they have here now. 2/3 to the x, 1/2 to the x, 1/3 to the x. Okay, so they all go like so, and they all go through 0, 1 once again, which makes sense because we already know anything to the 0 is 1. Okay, look on this side, on the right side here, okay, and look at the progression. This is base 2/3, and then 1/2 and 1/3. So, and you can see if you plug in 1, right? What's 2/3 to the 1? 2/3. What's 1/2 to the 1? 1/2. What's 1/3 to the 1? 1/3. So 2/3 is bigger than 1/2, which is bigger than 1/3. So the red is above, and the yellow is the smallest. But notice again, on this side, they reverse. Okay, so both these kinds of graphs and these kind of graphs, the one that's highest and the lowest switch at 0, 1. So notice the red is the smallest here, but the biggest on this side. Okay, the green, I think that's green. Yeah, the green one is the biggest here, but it's the lowest here. Same thing over here. So let's see. On this side, the red is the lowest. So on this side, it's the highest. And likewise, on this side, it looks like the yellow is the highest. So after it passes the common point of 0, 1, it becomes the lowest. All right, and it looks like we have a little role reversal here. So these functions are decreasing. They're always going down. Okay, so if you have a fraction, something between 0 and 1, like base is 2/3, 1/2, 1/3, they're all decreasing. Okay, so this time when x gets big, y approaches 0. Okay, so if I plug in, let's say 1,000,000, 2/3 to the million, 2/3 times 2/3 times 2/3 times 2/3 times 2/3, 1,000,000 times is practically nothing. But if we go this side, okay, now recall if you have a negative exponent, you flip it and make it a positive exponent. So let's say 2/3 to the negative million. Flip it, you have 3/2 to the million, and that shoots to infinity. Okay, so on this side, when x approaches negative infinity, y approaches positive infinity. But when x approaches positive infinity, the y approaches 0 in this case. Okay, so that's what we have there. Okay, so on our graphs, we're going to be doing stuff we've done before, like compare 2 to the x minus 3. Okay, so 2 to the x, we know it looks sort of like that. And what's the effect of that minus 3? Shove the graph 3 units down. So like take the nice point 0, 1 down to 0, -2, and have the horizontal asymptote, which used to be the x-axis that has equation y equals 0, shove it down to y equals -3, like so. Okay, so we're doing stuff like that. Okay, on the top of 284, let me show you that. See if I can aim it so the focus is better. Oh, it's a little bit better. Okay, y equals 2 to the x. 3 times 2 to the x. Well, you just triple the value. Stop and think about it. If you plug in 0 here, you get 1, right? If you plug in 0 here, you have 1 times 3, which is 3, so it's higher. So that stands to reason this one will be a little bit higher. Okay. Now, what are they trying to show here? And it's kind of yellowish. It's hard to see. There we go. This is much better, but I have to hold the book up, so I can't keep it here that long. 3 times 2 to the x minus 1. Okay, 3 times 2 to the x. So if you replace x by x minus 1, we've done that before, that moves the graph 1 unit to the right. So the new graph of 3 times 2 to the x in red, that red matches this red, move 1 unit to the right. So 0, 3 becomes 1, 3, and just draw the same general shape. Okay. Now what are they trying to show over here? They're trying to show the progression of y equals -3 times 2 to the x minus 1. Okay, so the negative means it's going to go down. They had it coming down like so. And what they did was just reflect it across the x-axis. So 3 times 2 to the x minus 1, -3 times 2 to the x minus 1. Okay, so just reflect across the x-axis. And then plus 1, move the whole thing up 1 unit. So instead of the asymptote being the x-axis or y equals 0, it becomes y equals 1. Okay, so that's just a review of a lot of stuff we did before. Okay, so now I want you to be comfortable with something called e to the x. You're going to do base e a lot. Okay, what is e? E is like 2.718 and so on. Okay, this is on page 287. So let me just get the calculator here. Okay, we're not going to do that much with the calculator right now, but just to show you. So you should have a button on your calculator that says e to the x. On my calculator, it's next to something called ln. So just make a note of that. I mean, you don't have to get a calculator out now if you don't want to, but just make a note of it. There's ln, which stands for natural log or log natural, natural log. Okay, and above it is e to the x. There's a special button for that. There's also log and 10 to the x, which your calculator should have also. Okay, so standard calculators have just 2 bases for logs. Okay, log base 10, which is just regular log, and log base e, it's the base for natural logs. Okay, and you can't really forget the base because if you look right above, you look at log, right? Say, I wonder what's the base. Just peek up here, 10. And ln, I wonder what's the base. Just peek up here, it's e. Okay, now what is the number e? Okay, some calculators there actually is a button for e. I don't see it on mine. So if you have a button for e, you can just hit it. But on mine, I can trick it by saying e to the first power. So see how I'm, whoops, sorry. If I aim it wrong, I blind out your eyeballs. E to the 1. Okay, so there we are. 2.71828, blah, blah, blah. So E is like 2.7. It's an irrational number like pi. Pi is like 3.141, blah, 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 but there's infinitely many digits. E is like that too. It's an irrational number, and it's about 2.71828. So when I go e to the x, when I do e to the x, it's like 2.718 and so on to the x power. Okay, and you notice in the graph, okay, here's 2 to the x. I'm not sure if you can see it, but the red is 3 to the x. Yeah, this focus is fine, but I have to hold the book up. And then the one between those is e to the x. So can you see that yellowish one, e to the x? That makes sense. It's like 2.7, so it stands to reason to be closer to 3 to the x than 2 to the x, I guess. Okay, so 2 to the x in blue, 3 to the x in red, and in between them, I guess that's yellow, is e to the x, 2.718 to the x power. Okay, so here are some properties of e to the x and e to the negative x. Okay, e to the negative x is decreasing, which you can also write as 1 over e to the x, right? 1 over e to the x is the same as e to the negative x. It's a decreasing function. All right, so take a look at these two graphs. The domain is all real numbers. They call it f and g. So f is e to the x, g is e to the negative x. So the domain is all real numbers. The range is a set of positive real numbers, or we can say 0 to infinity. So if you look at this graph, it never actually touches the x-axis. It doesn't touch the x-axis. Same thing here. It doesn't touch the x-axis. Okay? So you can have anything for x for both of these, but y has to be positive. So that means e to the anything is positive. The exponential function only returns positive values. Okay, what's the y-intercept? 0, 1. Y-intercept is always 0, 1. Okay, as you can see, e to the x is always increasing, always going up. E to the negative x is always decreasing, it's always going down. And that's true for any of these. Let me just reinforce that with what we had here. Okay, so if the base is bigger than 1, the base is bigger than 1, the graph is increasing. If a is less than 1 but bigger than 0, so we're going to say between 0 and 1, the graph is decreasing. It's up to you if you want to put this on your next cheat sheet, you may. Okay, so decreasing if the base is smaller than 1. But again, bigger than 0. We're not going to deal with negative exponents. We're not going to deal with a base of 1 because 1 to the x, 1 to anything is still 1. So no reason to really talk about it. Okay, and let's see. The graphs of y equals e to the x and y equals e to the negative x have the x-axis as a horizontal asymptote. Okay, so you have an asymptote here. Difference is that for e to the x, the asymptote shows up when you go to negative infinity, right? When you approach negative infinity, then we get close to the x-axis. For e to the negative x, when x approaches positive infinity, e to the negative 1,000,000 is almost 0, going to positive this way, but this way, when x approaches negative infinity, y approaches infinity. Okay, and it turns out they are the reflection about the y-axis of each other. Okay, so in other words, if I take the graph of e to the x right here, try to do the mirror image like so, it ends up being this one, and vice versa. The mirror image of e to the negative x, if I reflect there, it ends up being this graph. Okay, so for e to the x approaches infinity as x approaches infinity. So when x gets big, y gets big. E to the 1,000,000, e times e times e, 2.7 times 2.7 times 2.7 times 2.7 1,000,000 times is super big. E to the x approaches 0 as x approaches negative infinity. So when I go way out that way, right, then y values approach 0. E to the negative 1,000,000 is like 1 over 2.7 times 2.7 times 2.7 1,000,000 times is a super small number. Okay, then of course you have the role reversal here for e to the negative x. E to the negative x approaches 0 as x approaches infinity. It's sort of like what we just said. So e to the negative 1,000,000 is almost 0. That's why it's going like that. but e to the negative x approaches infinity as x approaches negative infinity. So if we plug in negative a million here, you'd have e to the negative million. That's e to the positive million. So that becomes very, very big. Okay, and then a quick review of properties of exponents that you should already be familiar with. I think I can raise it up. Yeah, I'm learning this is much better for focus, but I have to hold the book up, and I don't want to hold it up all the time. And I can't point either. So e to the x1 times e to the x2 is e to the x1 plus x2. So you know you can add these exponents. Let me look at the last one. E to the x1 over e to the x2, you subtract e to the x1 minus x2. Is that right? And then the power property, if you multiply e to the x1 raised to the x2, you have a power, and then another power on top of that, you just multiply the exponents, e to the x1 times x2. Is that right? Okay, so that's the way that works. Okay, so most of the rest of the problems, you take e to the x or 2 to the x or 2 to the negative x, and you just move it left, right, up, down, reflect, and all that kind of stuff. Something that we've done before, right? So that's what we're doing right now for today and tomorrow. So 1 to 19, it should not be that long to do these, hopefully. Okay? So I'll do 1 or maybe 2, and then I'm done for the day. I haven't done any homework problems yet, but that's okay. I don't think I have to. And then, yeah, you might have a question later about Math 251 or Math Jam or whatever. I'll take those up, and if not, then we'll just finish. Okay. All right, so now we can get started with some of this. 5.2, 1 to 19, skip 35 and 37. So I decided not to do it. Sketch the graphs showing any horizontal asymptotes. We're not going to have any vertical asymptotes. Okay, so stop and think about what's going to happen for 2 to the x and then 2 to the x plus 1. Okay, so I've got the answer that I'll show you in just a second. But remember, 2 to the x. So that's a base that's bigger than 1. That fits this category. So roughly speaking, it's going to increase, go like that, passes through 0, 1. And then you should know what happens to, whoops, plus 1. Move 1 unit up. Okay. So here we go. And first, this is my quick version, the Melvin Hom version of exponential functions. So f of x equals a to the x. A is greater than 0. A not equal to 1 is called an exponential function. Okay. Please notice the base is a constant. The variable is an exponent. So here are some examples of exponential functions. 2 to the x, 3 to the x, e to the x. E is about 2.718. I showed it to you earlier here, right? And your e to the x is normally above the ln right there. 10 to the x, 1/2 to the x, 1/3 to the x. You don't have to write these down if you don't want to, but they're just examples. Please notice these are exponential functions. The base is a constant. The variable is floating up here. It's not the other way around. So it says x squared, that's not considered exponential. X cubed, x to the 10, x to the half. Those are not considered exponential functions. Those are power functions instead, P-O-W-E-R, power functions. I'm not even going to write that down. You don't have to worry about it right now. Okay, so let's say, how do you graph f of x equals, I didn't even write it down, 2 to the x plus 1. Okay, so first I consider 2 to the x. Okay. Let's say, how do you come up with a graph? You can make a table. Okay. You can see I made a table. I just plug in -3, -2, -1, 0, 1, 2, and 3. So looking only at 2 to the x right now, just saying, how do you come up with this graph? Plug in 0. 2 to the 0 is 1. 2 to the 1 is 2. 2 squared is 4. 2 cubed is 8. Plug in -1. 2 to the negative 1 means 1/2, 1 over 2. 2 to the negative 2 is 1 over 2 squared, which is 1/4. 2 to the negative 3 is 1 over 2 cubed, 1/8. Okay, so if you were to plot them all, you would get something like the red graph, 2 to the x. All right, then 2 to the x plus 1, move the whole graph 1 unit up. Okay, so 0, 1 just becomes 0, 2, and I just draw the same basic shape. So the green is the answer to the problem, 2 to the x plus 1, and it asks for the horizontal asymptote. So the horizontal asymptote used to be the x-axis, or y equals 0, right? So I just move it up 1 unit. So the horizontal asymptote, HA, is now y equals 1. Yet I will not accept just 1. You have to say y equals 1. That tells me it's a horizontal line for the horizontal asymptote, of course. Okay, so the final answer, yeah, I needed the red just to set up, but the final answer is the green, 2 to the x plus 1. Okay. All right, I was going to show you number 3 and then stop, and that's it. So I'll be done in a few minutes, at which point you can either ask me questions, or if not, we can just quit. Okay, so negative 4 to the x. So I'll just take positive 4 to the x. And what does a negative do? It makes the positive negative, so it just reflects across the x-axis. Okay. So let me get that for you right now. So number 3, negative 4 to the x. Okay, so positive 4 to the x generally looks something like this. Here's a real quickie table. I didn't do very much at all. If you plug in 0, you get 1. We already knew that, right? 0, 1. Plug in 1, you get 4. So 1, 1, 2, 3, 4. Plug in negative 1, 4 to the negative 1. That's 1 over 4 to the positive 1, or 1/4. It's kind of hard to graph it, but it just goes 1/4 there. But we already know it looks like that. Okay, negative 4 to the x. If you stop and think about it, for negative 4 to the x, it's exactly the same as 4 to the x, except I have a minus sign for all of these, right? So instead of 1/4, it would be negative 1/4. Instead of 1, it'd be negative 1. Instead of 4, it'd be negative 4. So it ends up looking like this. So yes, it is just a reflection across the x-axis. Okay. So the graph of negative 4 to the x looks like this. So here's 4 to the x, here's negative 4 to the x. Okay. All right, and I am done, folks. So let me stop the share. Check. Okay, let's see. A question was brought up about extra credit. Sorry, there's no other extra credit. And the reason for that, I'm so mean about that, is to me, you already have extra credit from participation, where you don't really have to do anything extra except just don't do anything that I don't like. Okay. And to me, the quizzes are almost extra credit because they're not really quizzes, right? Normally, what do you think of as a quiz? Well, you get 15 minutes, 20 minutes. You can't help each other out. But you can talk each other out. So, yeah, sorry, I'm not giving any extra credit, because to me, participation is already extra credit. And the quizzes are also sort of like extra credit. So nothing additional for that. Okay. And let me see what else there was in the chat. I don't think there's anything else. Okay. So does anybody want to ask me any questions about this section, or about Math Jam or Math 251 or anything on that? You don't have to. If not, we can just call it a day. So I'll wait just for a few seconds. Anybody else? What is Math 251? Math 251 is Calc 1. It's not Applied Calc. Applied Calc is Math 241. Okay, Math 251 is the harder calc sequence. So the easier calculus is Applied Calc. That's Math 241. Okay, Math 241, you don't have to have Math 222 as a prereq. Okay, it's for different majors. Okay, this is the calc for engineering, computer science, math majors, physics majors. It's definitely a harder calc. And the reason why you're taking pre-calc is so you can take the harder calc. All right. Anybody else, please? All right, then we'll call it a day. I mean, you can still ask questions tomorrow or the next day or whatever. That'll be fine. All right, have a good day, everybody. We'll see you next time. Bye.